Good morning, students. Good morning, math enthusiasts. Today, we are going to discuss about proving geometrical statements using concepts and circles. There are many concepts and circles, so that it is important that we divide our video into two parts. So this is part 1. Again, the principles and circles as well as its examples were taken from Shom's outline in geometry. The illustrations as well as the flow of the proof were made by yours truly. Let's start with the definitions. A circle is a set of all points in a plane that are at the same distance from a fixed point called a center. So this is a circle, and this is the center of the circle. The circumference of a circle is a distance around the circle. It contains 360 degrees. So these actually, the points, form the circumference of the circle. A radius of a circle is a line segment joining the center to a point on the circle. So we have here the radius joining the point and the center and a particular point on the circle. So if we have more than one line, if we have more than one of this, daghan siya diri, then we call it now as a radii. So note that since all radii of a given circle have the same length, we may at times use the word radius to mean the number that is the length of the radius. A central angle is an angle formed by two radii. So we have here two radii, then we have formed an angle, angle AOB and angle BOA, which of course is a central angle. An arc is a continuous part of a circle. So the circumference happens to be the arcs as well. And so we have here this arc or this arc AB. A semicircle is an arc measuring 1/2 the circumference of the circle. So if we have here this particular line segment, and then this arc here, which is 1/2 of the whole circumference, is a semicircle, and also this arc is a semicircle. To intercept an arc is to cut off the arc. So as you notice here, this is a semicircle, and then if we cut off that arc, particularly here using a radius, then we intercepted that arc. So we intercept arc here, BC. A chord of a circle is a line segment joining two points of the circumference. So notice points C and D, and then if we connect that using a line, so this becomes a chord. We have chord CD. A diameter of a circle is a chord through the center. So notice that this was shown beforehand already. So this is a chord that passes through the center, and so it's called a diameter. And this is a longest chord, the longest chord. A secant of a circle is a line that intersects a circle at 2 points. So if you notice here, there are two lines. So which is the secant of a circle? Okay, so this is the secant of the circle because it passes through the circumference of the circle at 2 points. Now what is this line? This is a tangent of a circle, which is a line that touches the circle at one and only one point, no matter how far produced. So notice that this line intersects the circle at only one point, so it's the tangent of the circle. And this is the secant of the circle. An inscribed polygon is a polygon all of whose sides are chords of a circle. So this is a polygon, particularly a pentagon, and notice that the sides are all chords of circle O, and it's called an inscribed polygon. A circumscribed circle is a circle passing through each vertex of a polygon. So notice that this circle passes through the vertices of pentagon ABCD, so that this circle is called a circumscribed circle. A circumscribed polygon is a polygon all of whose sides are tangents to a circle. So notice that this is a polygon, particularly a triangle, and its sides passes through the circle at only one point, and so these sides are tangents, and so it's called a circumscribed polygon. An inscribed circle is a circle to which all the sides of a polygon are tangents. So this circle here is an inscribed circle because of tangents AB, BC, and AC. Concentric circles are circles that have the same center. So notice that there are two overlapping circles here, the small circle and the big circle, and they of course have the same center. So this is line segment OA, which is the radius of the small circle, and line segment OB, which is the radius of the big circle. Two circles are equal if their radii are equal in length. Two circles are congruent if their radii are congruent. So we have here two circles, and if r sub 1, the radius here, is equal to r sub 2, the radius in this other circle, then these two circles must be equal. Or if radius 1 is congruent to radius 2, then these two circles are congruent. Two arcs are congruent if they have equal degree measure and length. So notice that arc AB is congruent to arc CD if these arcs have the same measure or length. Principle 1. So we will now be discussing about circle principles. So to start with, we have principle 1. A diameter divides a circle into two equal parts. So diameter AB divides the circle into two equal parts. Principle 2. If a chord divides a circle into two equal parts, then it is a diameter. So this is the converse of principle 1. Recall converse? Okay. So if this chord divides the circle into two equal parts, then this chord must be a diameter. Principle 3. A point is outside, on, or inside a circle according to whether its distance from the center is greater than, equal to, or smaller than the radius. So notice that point P is inside the circle. So if we connect a line from point P to O, then this line segment must be less than the radius. Now point Q is on the circumference of the circle, and if we connect a line to these 2 points, then this is another radius or equal to the given radius OA. Now point R is outside the circle, so if we connect this point to this point center, then we have a line segment that is greater than the length of the radius. Principle 4. Radii of the same or congruent circles are congruent. So if we have here a circle and there are two radii, so these two radii must be congruent. Now if we have another circle and this radius happens to be equal to the measures of this radius, then these two circles must be congruent circles. So actually, if these two circles are congruent, then these radius or radii are congruent. So that's principle number 4. Diameters of the same or congruent circles are congruent. So if notice that in this circle, its diameters are of course congruent. Now if these two circles are congruent, then its diameters are congruent. So diameter EF is congruent to any of these two diameters. In the same or congruent circles, congruent central angles have congruent arcs. So notice that if these two central angles in a circle are congruent, then its arcs must also be congruent. Now if these two circles are congruent, then and also these central angles are congruent, then these arcs are congruent. Principle 7. In the same or congruent circles, congruent arcs have congruent central angles. So this is the converse of the previous principle. Principle 6 and 7 are converses of each other. So that if we say these arcs are congruent of congruent circles, then these central angles must be congruent. Principle 8. In the same or congruent circles, congruent curves have congruent arcs. So within a circle, if these chords are congruent, then its corresponding arcs, intercepted arcs, are also congruent. Now if these two circles are congruent and these chords are also congruent, then these arcs must also be congruent. Principle 9. In the same or congruent circles, congruent arcs have congruent chords. So this is the converse of the previous principle. Principle 10. A diameter perpendicular to a chord bisects the chord and its arcs. So if this is a diameter which is perpendicular to this chord, then it must imply that it also bisects that chord. So line segment AD is congruent to line segment BD, and furthermore, it bisects the arcs here, ACB, arc ACB, so that arc AC is congruent to arc CB. Principle 11, a perpendicular bisector of a chord passes through the center of the circle. So this is the converse of the previous principle, so that a perpendicular bisector of a chord, so if this chord is perpendicular to this chord and then it bisects this chord, then that chord must be a diameter, or it passes through the center of the circle. In the same or congruent circles, congruent chords are equally distant from the center. So in the same circle, if congruent chords here must be equally distant from the center of the circle. So if these are congruent circles, then if these chords are congruent, then they should be measuring the same distance from the center of the circle. In the same or congruent circles, chords that are equally distant from the center are congruent. So these are the principles 12 and 13 are converses of each other. So this is the converse of principle 13, such that if these chords are equally distant from the center, then these chords must be congruent. If these chords are equally distant from the center, then these chords CD and AB or EF are congruent. Let's start with example 1, which was again taken from Shom's outline in geometry. So suppose that you are given that line segment AB is congruent to line segment DE and line segment BC is congruent to line segment EF, then we have to prove that, or you have to prove that angle B is congruent to angle E. So let's start with the markings. We were given that line segment AB is congruent to line segment DE. We were also given that line segment BC is congruent to line segment EF. And we need to prove that angle B and angle E are congruent. So how are we going to do this? So normally we think of our triangle congruence, but probably we can think of another way. So as you can see, recalling the previous principles, if these chords are congruent, then what can you say about the intercepted arcs? So the arcs must also be congruent. Now if these chords are also congruent, then these arcs must also be congruent. So why not think about the triangle congruence? Why think about these arcs? Because as you can see, these chords here will be congruent because of these arcs, right? So if we add these arcs, which happens to be correspondingly congruent here, so these chords must be congruent. So what happens now after that? So notice that in these two triangles, we have three corresponding parts that are congruent already. So we may now start thinking of SSS postulate. So by CP/CTC, these angles must be congruent. Okay, so let's have the formal proof. Line segment AB is congruent to line segment DE given, and it means that arc AB is congruent to arc DE. So I'm sorry with the notation because I think there's something wrong with the software here, because the notation used from the equation was actually arc, but it's changed in the actual already. So arc AB is congruent to arc DE because congruent chords have congruent arcs. Also, another given, line segment BC is congruent to line segment EF, and its consequence is that these arcs are congruent. So arc BC is congruent to arc EF because congruent chords have congruent arcs. Now, as I've said, we can add these two arcs. So arc ABC is congruent to arc DEF because if equals are added to equals, their sums are equal. And so, as a consequence of statement 5, which is statement 6, there's a problem with the numbering. So it's statement 6. Line segment AC is congruent to line segment DF because these are chords. So congruent arcs have congruent chords. So now we have three corresponding parts. So triangle ABC is congruent to triangle DEF by the SSS postulate. And as a consequence, we have the conclusion. Angle B is congruent to angle E by CPCTC or CACTC. QED. Example number 2 was again taken from Shom's outline in geometry. Prove that if a radius bisects a chord, then it is perpendicular to that chord. So the hypothesis is a radius bisects a chord, and the conclusion is that radius is perpendicular to the chord. So from there, let's have our figure or illustration. A radius bisects a chord, so we draw a radius OC and then a chord AB. And so it should bisect chord AB. Now, as a conclusion, is perpendicular to the chord. Okay, so let's create the restatement. So we are given a circle O with, of course, center O. Then OC, line segment OC, the radius bisects line segment AB, our chord. Now we have to prove that perpendicular man siya, that line segment OC is perpendicular to line segment AB. So let's have the marking. So when we say line segment OC bisects line segment AB, it implies that line segment AD is congruent to line segment BD or DB. Also, we should prove that line segment OC is perpendicular to line segment AB. So this is going to be our direction. So how are we going to do that? How are we going to make these two lines perpendicular? So first, we should make these two angles right angles. And how is that possible? That's possible if we have two triangles. Let us create line segment OA and line segment OB, which are actually the radii of the circle. So we have two triangles already. And the radii of a circle are congruent. Also, by reflexive property, line segment OD is congruent to itself. So notice that we have three parts already. So that means we can prove that these two triangles are congruent by the SSS postulate. And these angles are congruent by CPCTC. And these angles to be congruent and by the concept of supplementary angles should be right angles. So let's have the formal proof. Let's start with what we are given. Line segment OC bisects line segment AB, given, and that the consequence is line segment AD is congruent to line segment BD by the definition of bisect. And by construction, so we have line segment OA and line segment OB are congruent because all radii in a circle are congruent. And by reflexive property, line segment OD is congruent to line segment OD. So we have three parts already, and so triangle ADO is congruent to triangle BDO by the SSS postulate. And so, angle ADO and angle BDO are congruent by CPCTC or particularly CACTC. Now, notice that angle BDO is supplementary to angle ADO because adjacent angles are supplementary if their exterior sides lie on a straight line. So, angle ADO and angle BDO are right angles because two angles that are congruent and supplementary are right angles. And so, line segment OC is perpendicular to line segment AB because perpendicular lines are formed by right angles. QED. Okay, that's all for today. We will have the next part of the concepts of circles in our next video. So thank you very much, and remember, math is easy to learn when one learns with enthusiasm. Bye!